welcome back, everyone. So in the break, we will actually take a picture outside here. So don't run away in the next break before you take your coffee. Let's go outside real quick. Good. So we have a bunch of experimental talks this afternoon, and we will open the session with Christie Chiu from our lab, who will be talking about string patterns in the doped Hubbard model.
Yep. Great, thank you, Marcus. Yeah, so as Marcus said, I work in his group on the Fermi gas microscope, and you heard before lunch from Fabian a wonderful talk on looking at geometric string patterns in spin systems, and so this is kind of the experimental counterpart to that talk. So I'll start by motivating this. Of course, with this audience, I feel like I really need no motivation, but talking a bit about quantum simulation. And one of the notable examples is if you look at these cuprate materials, which have a structure which looks somewhat like this. And these cuprate materials have been very thoroughly studied. For example, the phase diagram with hole doping or particle doping, and also temperature. And very many interesting phases have been observed. And the thing is, with many of these phases, there are still many open questions. And so if you look more closely at these cuprate materials and you were to try and distill it down maybe to a toy model or something that's a bit more similar, easy to study, then you'll notice that if you look just at the copper atoms, they form these 2D planes with this square lattice structure. And so that then motivates looking at ultra-cold fermions in an optical lattice, an optical square lattice. And here we can write down the exact microscopic model. So we have this Fermi-Hubbard model that has a tunneling term. Particles can tunnel from one site to a neighboring site. And then we also have an on-site interaction term. And this is something that, for us, we use lithium atoms. And so lithium has a very broad Feshbach resonance that makes it very easy for us to tune this interaction to be either attractive or repulsive. For everything that I'll mention in this talk, we look at the repulsive Fermi-Hubbard model, so we tune our interactions so that U over T is about 8. All right, and so now the idea is that we can, by looking at this system, we can learn more about these cuprate materials and more broadly strongly correlated materials. I should also mention that a great deal of work has been done in these types of systems by basically everyone in this audience, starting with the cold atom proposal in 2002, and then looking at ultra-cold fermions and optical lattices starting in 2008, and then with the advent of Fermi gas microscopy in 2015, this has kind of really taken off. So one quick slide on Fermi gas microscopy. Again, we heard a lot of already kind of what this is, but the idea is that we can load a 2D plane of a 3D optical lattice with a balanced spin mixture of fermionic lithium-6. And we have, 2 spin states, and then we can kind of tune the interactions, have time evolution, and then we can pin all of the atoms in place and then image it with a high-resolution microscope, and we too have a very nice mod insulator. So, I add my picture to the ones that have been presented yesterday. So, these, of course, are kind of very early images. We should maybe update them, make an art gallery, something like that. So, but the idea is that, with this site-resolved control, you can now access many more observables at the local level. So the title of this workshop is focusing really on the low temperature frontier. And so I wanted to talk a bit about that. So at high temperatures, you can have charge excitation. So you can have particles that are thermally excited. And so that gives you this metallic state where you have particles that are tunneling and moving around quite nicely. But as you get to colder and colder temperatures, if you can push this temperature below the interaction and the limit where the interactions are larger than the tunneling, then you can start to see charge order. And so that's where, for example, you can have a mod insulator where everywhere it's energetically unfavorable to have 2 particles per site. And so you see exactly 1 particle on every single site. But if you can get to even colder temperatures, lower than the exchange energy, which is the energy for two particles to swap places of opposite spin, then you can start to see spin order in the system. And so one of the long-standing challenges for these quantum gas microscopes is to reach these colder and colder temperatures. And really only once you are on the order or below the super exchange energy can you start to access the physics that is seen on this phase diagram. And so to reach lower temperatures, what we do is we first take note of the fact that when we create our optical lattices, they're retroreflected. And so that means not only do we have our lattice potential, but we also have this underlying harmonic potential. And you can see that with this cartoon here, and then with an atom distribution here. But then what we do is we install this digital micromirror device, which really allows us to tune the potential on every single site. And the idea is we really just use this imaging system exactly in reverse. So if we can image on the site result level, we should also be able to project patterns on the site result level. And so as a first implementation of this DMD, what we do is we create a pattern which looks more like this. And this is something which is very flat and homogeneous in the center. And so we know that the local chemical potential is constant here. And then we have it thermodynamically coupled to what we call a reservoir that's on the outside. And this has a much lower chemical potential. And so you can see in the atom distribution, we can realize a state that's at half filling, 1 particle per site in the center, surrounded by a very, very dilute cloud. And the idea here is that with this technique, we can actually achieve very, very low entropies per particle in the center. And that works in the following way. So imagine you have 2 harmonic oscillators with very different harmonic oscillator energies. If you now put the 2 in thermal contact with each other, then you see that the number of states that are populated in each of these wells is very different. That is to say, if you have a harmonic oscillator with very high density of states or very low-lying excitations, then you'll populate many more states compared to a system where you have a very low density of states, or it costs a lot of energy to create an excitation. And so if you were to add an excitation in the system, it would probably go to this side over here. And so then, of course, we can label these as our reservoir in our system. And so then if we go back to our picture, then we see that our system is the one in the center where we have 1 particle per site. There's a very low density of states compared to the metal, which is on the outside and has a very high density of states. And so now if we were to take pictures which look like this, but instead we were to remove one of the spin species prior to imaging, then sometimes we can get images which look like this. And this is something that has also been shown earlier in this workshop, this exact same image. But the idea is that now if you were to binarize this image and very suggestively overlay a checkerboard, then you can see that these spins really do follow this checkerboard type antiferromagnetic order. But of course, even in a quantum system, even if you were at 0 temperature, you would not expect to see a checkerboard every single time. And that's really because of the quantum nature of the antiferromagnet. And so instead of taking pictures and looking at single images, in order to characterize the antiferromagnet, we need to look at other observables. And so one of these is the staggered magnetization. And so that's looking at basically how checkerboard-like this image is. You get like 1 point for every spin that's on the right sublattice, and you lose 1 for every one that's on the wrong sublattice, and then you normalize to your system size. And we can actually calculate this value for every single snapshot that we take and get a full counting statistics histogram of what the staggered magnetization is. We can, of course, also look at correlation maps. So now what we do is for any given vector distance, x, y, we can look at sites within our system that are exactly that distance apart and see what is the average correlation across that distance. Oh, that's in the wrong order. So that gives us this map where here we see that nearest neighbors tend to be very strongly anti-aligned with each other, this negative correlation, and then diagonal nearest neighbors tend to be aligned with each other, and really this antiferromagnetic character extends all the way to the edges of the cloud. We can take an azimuthal average of this and do a more quantitative study. We fit to a long wavelength theory. And really what I want to point out here is the nearest neighbor correlator. So here it's been corrected for which sublattice it's on. So now it's looks positive. But really, this is the most quantum part of the antiferromagnet and reflects a strong degree of singlet character in your 2D antiferromagnet. This is also the value that we use as our thermometer. So at half filling, quantum Monte Carlo data is available. And so by looking at the value of this correlator at half filling, we can extract a temperature. And here we have our lowest temperatures to date, temperature in units of the tunneling of about 0.25. So at this point, we've just entered the antiferromagnet regime here. We're at half filling still. And so at this point, we actually have a lot that we can do. We can already start to dope the system, for example, and try and see what physics there is to study, or we could push towards even lower temperatures. And so today, I'll talk about the former, looking at what happens when you now start to dope this antiferromagnet at temperatures that are about 0.25 times the tunneling or 0.5 times the superexchange. And so to motivate this, again, I want to go back to these observables and mention that these are kind of the conventional real space observables that we see and that we've been using. So order parameters or correlation functions. And so the thing is, though, if you look at the pictures that come out of these quantum gas microscopes, you have a lot more information there. And so the question is, what about new observables? Are there new observables that you can come up with or that you can try and extract from all of these images, and in that way learn more about the physics that's going on? And so to do that, we can look at exactly what Christian talked about and also what Fabian talked about earlier this morning, and see what happens when you have holes in the Hubbard model. So in one dimension, as Christian said, we have spin charge separation, which is to say, as you have this hole that's moving around, if you were to remove that hole at any point and look at the spin background, it looks exactly the same. However, in 2 dimensions, this isn't quite the case. If you now take the hole and you move it around, you see that it leaves a very distinct pattern of spins in the path that it took. And so that's to suggest that in 2 dimensions, we instead have this complex interplay of the spin and the charge degrees of freedom. It's also to say that if you were to somehow know the pattern of where all of these holes moved, then you could exactly go back to half filling. And so the motion of these holes really provides a relationship between the half filling parent antiferromagnet and your doped antiferromagnet. It really doesn't say anything about the half-filled antiferromagnet to start. And so I don't need to go in depth for the theory, but what I'll say is, if you now look at this as an entity, you see that it is, or you can describe it as a bound spin-on charge-on pair with a length that depends on your Hubbard parameters and also your temperature. This idea isn't completely new. It goes back to the 1960s in some form or another, but it's really been kind of resurrected more recently and really fleshed out. And one thing to note is that while this charge-on moves very quickly with the timescale of tunneling, this spin-on moves very slowly because it requires spin exchanges in order to move. And so the idea is that even at equilibrium, we may be able to detect signatures of these geometric strings. And so what we'll look at in this talk will be at equilibrium. Okay, so if we want to look at these string patterns, then of course we can look at them within our experiment. And so we have our Fermi gas microscope, and we actually take about 30,000 measured snapshots with one of the spins removed. We can also, of course, compare to many theories. So there's this analytic geometric string theory. We jokingly call it string theory for short, that Fabian mentioned. And again, that tells you a relationship between your doped and your parent antiferromagnet. We can take, of course, a very much more naive theory, which is to say, what if these bound states are not stable, and instead we just have some holes that effectively have a string length of 1. So sprinkle some holes into your antiferromagnet, but they don't really do much to the spin order other than that. And then also, as Fabian mentioned, we can look at RVB-like states and also have a simulation which gives us individual snapshots and compare that to the experiment as well. I should note here the simulated strings, that just takes in exactly what temperature we have in our Hubbard parameters, so that's 0 free parameters, while for the RVB-like state, we actually fit to an effective temperature, so there is one free fit parameter there. And then for every single one of these, we get a set of snapshots, and then for every single set of those, we can run them through a single pattern detection algorithm. And so I want to stress the fact that this pattern detection is really common mode to all of both experiment and theory in this case. So how does this string pattern detection work? So I'll go through an example just with these cartoons. And let's say that they're from the microscope. And so we have a bunch of measured snapshots that have one of the spin states removed. For every single one of these images, we now compare to a classical nail state, a perfect checkerboard. And we ask, what are the sites that deviate from this state? And these are the ones, in this case, highlighted in yellow. Now, from this subset of sites, we can extract string patterns following certain rules. For example, none of the patterns have any branches to them, so they are indeed string-like. They have to be consistent with having a hole at one end of the string, and we tend to favor long strings. So in this example, we can run this algorithm and sort them according to their length. So for example, here we have one string of length 4, one of length 3, 2 of length 2, and 2 of length 1. And so the first thing that we can do is we can create a histogram of how many strings do we find at every single length. So if we do that for experiment, and first we do it at our cold temperatures at half filling, we get a signal which looks like this. And the fact that this histogram is not 0 across all string lengths reflects the fact that in our string pattern finding algorithm, we made the assumption that we're always comparing to a classical checkerboard. But of course, we know that's not true, because a quantum antiferromagnet is different than that. And so we should instead be thinking of this signal as a baseline level from the fact that we have, of course, non-zero temperature and incomplete information, but of course, all of these other things that are by far the largest contribution to this signal, which come from the fact simply that we have a quantum system. So now if we dope the system to, let's say, 10%, we can look at our histogram, and we see that the number of string patterns that we find across all lengths increases, and it's statistically significant. And so at this point now, we can, of course, compare to theory. And so to do that, we also need single snapshots that we can run through the same exact string pattern finding algorithm. And as I mentioned, the geometric string theory only provides a relationship between your parent AFM and the doped AFM. And so we need to seed it with what snapshots actually look like at half filling. And the best way to do that is straight from our microscope. And so we have, again, a set of measured snapshots that are now taken at half filling. And now we can put in strings almost by hand according to this geometric string theory. And that works in the following way. So again, for each snapshot, we artificially dope the system. So we randomly place holes regardless of whether there was a particle or a hole measured on that site, and regardless of what sublattice it's on. So we dope to whatever level we want. And then we look at this string histogram, and we basically pull from the histogram to figure out what string lengths are we going to create with the holes that we've put in. And so again, as a toy example, so this hole, for example, is length 3, so we moved it by 2 sites. Every time we move the hole, it's in a completely random direction, but it never goes backwards. And so here, there's a string of length 2, and then sometimes we have a string of length 1, and we just leave the hole as is and don't move it at all. So now if you were to look at the entire set of these images created, all from here, we can run this through the same string pattern finding algorithm and see what is the length distribution that we get at the end. And that we'll call simulated strings. We can also stop here right after artificially doping the system and not moving the holes around. And we can look at the effect of merely just placing these holes in, and we'll call that sprinkled. So again, if we look at this histogram, we can place the sprinkled holes in first, and if we look at where this lies, it does not explain the increase in the number of string patterns we find when we experimentally dope the system. By contrast, if you were to put in these simulated strings, you find that it matches remarkably well. And then if we look at this RVB-like state, or pi flux state, then we see that it also fits quite well in this observable. we can reproduce this experiment, but now we heat the system first, so we can do this at much higher temperatures. And we see that at these high temperatures, there really is no distinction that can be made. And that's to say that this observable is something that is really sensitive to being at low temperatures. Again, because in that first step in the pattern finding algorithm, we're comparing our pictures to this classical nail state. And so if you are at these very, very high temperatures, then that assumption, of course, obviously breaks down. We can also look at the total number of strings that we find as a function of doping. And so again, this is experimental data, and there's some baseline that's at half filling. But as we dope the system now, for very small dopings, we see a linear increase in the number of strings that we find. And this is consistent with the fact that for every single new hole that you're creating, you have a proportional linear number of strings that's also being created. But of course, as you go to very, very high doping values, then you see that there's a saturation in the number of strings that you find. And that can also be explained by this geometric string theory with a picture that if you now have so many holes in your antiferromagnet that they're moving around and they start to actually lie next to each other or cross each other, then no longer are they dilute and non-interacting, which was the assumption that was made in the geometric string theory. And so this could reflect the fact that the physics is now changing at this point. Again, we can compare to all of our theories, and we find that, especially quantitatively, the simulated strings seem to fit best across the entire range of dopings that we've considered here, all the way from 0 to about 35%. So not only can we look at the string pattern count, but it's also useful to look at the average length of the strings that we find, noting that many of them may be affected by the fact that we do have, for example, double on hole pairs or spin exchanges, which will bias you towards shorter strings. But again, if you do that, and I won't go into detail for the red and the orange points, we can talk about that later if you want, but if you look at the experiment, you see that the string pattern length is fairly flat across small dopings, but then tends to get shorter as you reach a doping value, which is pretty similar to where this starts to saturate. And so this would also support the idea that when you have dilute strings, they all operate exactly independently of each other according to the string length histogram. But once you have so many of them that they start to maybe interact with each other, then this is no longer the case. And this also fits well with the simulation. So of course, even though we've looked at these new observables, we should still continue to look at the more traditional observables. And so one of these is a spin correlation. And so here what we've plotted is, as a function of doping, what is the nearest neighbor spin correlator, sign corrected, and also what is the diagonal next nearest neighbor spin correlator. So at half filling, of course, we see that the nearest neighbor correlator is the strongest, and then it goes down as you dope, and similarly with the diagonal next nearest. If you were to look at the theories, again, I want to point out the fact that as you hit some critical doping, it does seem like this diagonal next nearest neighbor correlator experiences a sign change. And this is something which very clearly is captured by the simulated strings, but is not captured at all by the pi flux state. And so this is some qualitative feature which we see in only one of the theories. And you can understand this on an intuitive level by noting that, again, this nearest neighbor correlator is very, very strong at half filling. And so if you have that very, very strong correlator, well, when a hole passes through, if it shifts all the spins by one site, then that means sites that used to be next to each other are now diagonal from each other, which means that you have an admixture of this nearest neighbor correlator into the diagonal correlator. And once this becomes strong enough, then you see the crossing of sign for this value. We can also look at the histograms of the staggered magnetization. And if you look across all of these doping values, which span fairly extensively, then you see that the solid line does seem to match the experiment, the green, most closely, and that's exactly the simulated strings. So as an outlook, I wanted to show this image, which we took, which looks very similar to our are entropy redistribution images. But instead, in the center, you see that, well, it appears that there are all empty sites. But knowing the exact chemical potential, we know that there are actually 2 particles per site in the center, a perfect band insulator. And we can actually take many images of this to show that this, in fact, is not a lucky shot. And if we do that and average over about 100 images, we see that really in the center, we can create a band insulator with incredibly high fidelity. In fact, our occupation density, so the amount of defects that we have, is really 0.5%. And if you have 2 particles per site, then that corresponds to exactly 0 entropy per particle, because there has to be 1 spin up and 1 spin down. And so given this occupation density, you can calculate an entropy per particle, which is about an order of magnitude, or even more than that, lower than the entropy per particle in the antiferromagnet. And so this seems like it's an incredibly promising start to achieve these really low entropy states. So the challenge here now is to take this band insulator, to isolate it so that the entropy on the outside doesn't come in, and then to now somehow adiabatically change this trivial product state, this band insulator, into a strongly interacting, strongly correlated many-body state. We have already demonstrated that we can isolate the center very, very well, and we're currently working on kind of more sophisticated techniques to do this final step adiabatically. On top of that, we are also currently pursuing looking at the dynamics of holes on this 2D antiferromagnetic background. For example, if you have this bound spin-on charge-on pair, then you should see that when you first release that hole, it's going to move very quickly with the tunneling time until you start seeing that it's now bound by the spin-on at the other end, after which it should move more slowly with the time scale of this spin-on. And then, of course, as I just mentioned, these more advanced cooling schemes. I'd like to thank the group that did all of this work, so experimentalists, wonderful theory support, I should say, and yeah, I'd like to thank you for your time.
This simulated string seems to match all the experiments the best, except there was one.
Yeah, good. I'm glad you pointed that out. Yes. Yes, definitely. So, yeah, so the question is the simulated strings seem to fit all of the experimentally observables fairly well, except for one. And that's exactly this, right? The nearest neighbor spin correlator. And so we see that the experimental data seems to indicate that the spin correlations are actually still much stronger than what the strings would indicate. And so this could be several things. And one contribution might be the fact that the strings are there, or might be there, results in some back action of the spins themselves. So there might be some additional effects happening where, say, a hole passes through, causes a wake of destruction, let's say, but then the spin background responds to that. And so that might contribute to the fact that the experimentally measured correlators are indeed higher. And in fact, if that were the case, then you should also see the effect, but of course to a much smaller degree, for the next nearest neighbor correlators. And if you look here, again, it's kind of hard to say. The error bars are here, so they're very, very small. But it seems like, here we overshoot, and then here correspondingly we should undershoot if we actually have this mixing that's happening.
Yeah, so you mentioned the dynamics of the hole-ons and the spin-ons. So when you capture a histogram, how do you first make the holes? And then
yes.
How long does it take? And then how long does it take for you to make the image?
Yeah. So all right. So all right, okay. So this is the pattern that we use for the entropy redistribution. And so by basically tuning the amount of light that we have here, we can tune what our chemical potential is, and that will dope the system. So here in all of the experiments that I just spoke about, we tune the level here, and then when we load into the lattice, we also have this potential on. And so that kind of globally dopes the system.
So what's the time
Yeah, so our loading times are tens to 100 tunneling times. So the system is in thermal equilibrium. Is that
So
It's
I
not
your
thought,
question?
separate.
yeah, I thought the
It's not a separate
dynamics of the photons and holons was of order T initially.
Oh, I see, I see.
And so
Yeah, so
how do you make sure that the distribution that you measure, the histogram that you measure, is not in the middle of this dynamical process?
yeah, so the idea is that once you have this, let's say that when we load into the system, we have some holes. And every single hole initially is still moving very, very quickly. But once it goes a certain distance corresponding to this string length histogram, then it's now kind of bound. That's the length that it's bound to the spinon by. And so then, the entire center of mass of that system might continue to move, but the length of it should stay the same at that point. And so as long as we have about a tunneling time since introducing a hole, then we should be in that regime. And when we load, it's many, many tunneling
So
times.
the histograms don't change
So,
in time.
Oh, I see. So we haven't changed how quickly we load into the system, but of course that would also affect the fact that our spin distribution, our spin background, just won't be in equilibrium anymore. Instead, what we're currently looking at, and I don't have results presented today, but what we're looking at is deterministically placing a hole on a single site, let's say, and then you can let that go at time t equals 0, and then watch it move. And depending on how long you wait, you should be able to see exactly those timescales.
Very impressive results, Christie. I wanted to understand a little bit better the counting of the strings. So
Yeah.
you showed this one plot where there was only a small difference between sort of the background and the. Okay, can you get that?
Yeah. Of course. Yep.
Sorry, it was a lot of information.
Oh, sorry. Maybe I'll just show this one. Good?
Yeah. So I mean, the error bars are very small, but the fluctuations from, say, string length to string length are kind of large. So I would say that my gut feeling error bar would be rather shot to shot.
Yeah.
From one
Yeah.
dot to the
Yeah.
next.
So
and within that budget, it's a little tight. To
Yeah,
say
yeah.
that there's a significant difference.
Right. So I think I'll answer your question by addressing the fact that, yes, there is some structure that you see. It's almost like a zigzag pattern, right? And so that is actually something which is a result of the string pattern finding algorithm itself. It's something that Fabian very briefly mentioned when talking about the GMRG calculations and such. But basically the idea is that we always have some background that's happening, right? The fact that our antiferromagnet is quantum. And if you have a spin exchange and that happens to be next to a hole, then that's going to increase your size by a bit. And similarly, if you have a double on-hole pair, that'll increase your size by just 1. You kind of have to write it out, but basically there's some asymmetry between finding even length strings and odd length strings.
Okay, why is there a difference as a function of doping? So the dark green is the
Yeah.
the bright green is the
Yeah, and so that's exactly, yeah. And so the weightings of how that gets shifted is a function of your symmetry between the number of holes that you measure and the number of particles that you measure. If you measure half particles and half holes, then the probability of finding a hole at the end of some pattern is going to be lower than if you now start to dope the system and have an asymmetry. Yeah. We can talk about it more in detail. I think it involves cartoons.
Great results first. And you were mentioning as an answer actually to Barry's question that it might be that the discrepancy you see at this distance 1 correlator versus doping is due to back action. Naively, well, back action of the magnetism.
Yes.
So naively, I would have expected this to happen at larger distance, where you're not so much, the hole is basically close by and it's dominated by the hole, but if you're far away from the hole, the magnetism has more time.
Sure, yeah.
To destroy. My question is more: did you block? I mean, you have a signal at longer ranges. Did you make also comparison doping like spin correlator versus doping at longer?
Ah, I see. Yeah, so I don't have the plot here, but we did look at, say, just the spin correlation function at larger and larger dopings. And my recollection is that it seems to, all kind of work out.
It all works for the string theory? Only the shortest one is all.
Yeah, and so that's, I mean, you can think of it as, also if you do have super exchange, on neighboring sites, that's going to be, you're actually going to have super exchange. At longer distances, it's going to take a lot more time for them to talk to each other.
More short questions, and I saw you.
So, do you have any idea as to whether the next nearest neighbor hopping in your lattice can be non-zero? And I'll tell you the reason I'm asking this because there's been recent numerical calculations with non-zero next nearest neighbor hopping, where they find stripes. And if I'm not mistaken, they also find this antiferromagnetic correlations become ferromagnetic at some point, at some doping. And it's explained through formation of stripes. And if that's non-zero for you, I wonder if you can actually also see some stripes.
Right. Yeah. So for our parameters right now, it's very, very strongly suppressed. 2 orders of magnitude at the very least, something. But I mean, I think on the flip side, introducing a diagonal next nearest neighbor hopping would be very, very interesting. And so if we could just get that for free, then I wouldn't complain either.
I think the series experiment is actually exclusive to that.
Yeah, interfering.
See, I have quite a bit of difficulties. Now, you have mentioned the way that one map out the string, there are a number of factors I need to take into account. I mean, there are things like Dublon or rotation symmetry, and then you with that uncertainty, then you compare with the theory, which I imagine would also have some approximations, and the matching is very close. So what do I think? What am I going to interpret? Are you suggesting that this way of mapping out the spin strings is very accurate? Or
yeah.
And I actually, if there's uncertainty in the measurement, with some where the problem is actually quite fundamental, with the approximate theory, I wouldn't expect there's such a perfect match. But if there's such a perfect match, we wouldn't need the problem.
Yeah. So okay. So I guess there are a couple things there. So I would first say that this is this is just a start, right? It's the idea that there could be so much more information in these images than the observables that we all know and love, right? And so that's one idea, exploring that idea. On top of that, for the actual details for the geometric string theory that compared to, we have, for example, changed by hand. What does the string length distribution look like? What if we instead shift it to look something that is different? And again, I don't have the slides here, but you can actually look on arXiv now. We do a study of that and see, how do these observables change? And we do see that there is a quantitative difference if you were to change that. So, while I can't say this is proof of, any theory, right? That's incredibly, incredibly hard to do. We can say that, this is suggestive that it's a surprisingly good picture to be thinking about doped antiferromagnets at this temperature range.
Also one comment, this isn't like super precision comparison because you have to see the difference between those two isn't that large. I mean, it's a few error bars, but it's not like super high precision.
Yeah, it's only 30,000 pictures. Okay, great.
Yeah, okay, let's thank Christie.